All right, we started with quiz 6 before I turned the camera on. So there it is.
You like my doodles?
I have no clue, buddy.
Oh, name. Names.
Basically a bunch of doodles on my page.
Oh. Well, that is unfortunate. I mean, this will still get you something. I mean, but anyway, here it is. I'll do it. So first things first, this is equal to the magnitude of z times e to the I, the standard angle. So the magnitude of this is the square root of 2, because 1 squared plus 1 squared is 2. And if I picture this thing, it's at 1 plus I, right? So that is 45 degrees. So pi over 4 is theta. So we have root 2 e to the I pi over 4. In other words, my theta is equal to pi over 4. So the fourth root of z is the fourth root of the square root of 2 times e to the I pi over 4 divided by 4, right? In other words, it's the eighth root of 2 e to the I pi over 8. So there you go. That's the fourth root. And then z to the 1/4, remember, is the fourth root of z, then I fourth root of z, minus the fourth root of z, and then minus I fourth root of z. Because the fourth root of unity, e to the 2 pi I over 4, is e to the pi I over 2, which is cosine pi over 2, plus I sine pi over 2, which is I. So to get the fourth root of unity, you take the principal fourth root of unity, which I boxed there, and then you multiply it by zeta to the 4, zeta 4 squared, zeta 4 cubed, and that gives you those other things I just wrote here. Now, of course, I could explicitly write that in here, but since I didn't force you. I didn't say like write your answers in Cartesian form or write your answers in polar form. You could have written it like this. It would have been full credit. Right?
Did anybody get that?
Of course not. Yes. Yeah. Nobody got it because no one has done their homework yet, which is quiz 5, which is due Friday, which is 2 days from now. You have not done it yet. I can tell this from this. I mean, I'm just saying, if you've done your homework, like this would not be that mysterious. And I have done this particular root in class previously. Now, I understand I don't do it once in class and you automatically know it. I understand. I'm just saying that it is something we've talked about. All right, so just a heads up, we need to work on this. So our next topic is vectors. So how many of you guys have seen vectors before? 1, 2. So in your textbook, there's like a section on vectors, and it's not bad, but it has some poor notation, all right? And I will try to use the notation which is common to physics. So let's get into it. So a vector is basically, you could think of it this way, is it's a directed line segment. You could think of it as that. All right, you could describe a vector as a directed line segment. So it has a base point and a terminal point. All right, so like if this is the base point and this is the terminal point, then we typically draw the vector, we envision it as an arrow. It goes from the base point to the terminal point, right, like that, right? And so, one of the principal sort of subtle things about it as it's used is people will say things like, this vector is the same as this vector. It's got the same, if you start from here, it goes to there. So in other words, you could take this one, right? And you can imagine just moving it down to here without changing its direction, right? So-called parallel transport, right? And as vectors are used in physics, a lot of times we allow ourselves to move the vector around, right? So if you allow yourself to move the vector around, you're not really attaching the vector to a base point, let's say, all right? So that's just something to keep in mind as people use vectors. Not everyone insists on a base point being fixed. Like some people allow the base point to vary, all right? But to calculate a given vector, if you have a base point and a terminal point, you can calculate the vector, all right? And so let me just tell you how to do that. So if the base point is, let's say x1, y1, and the terminal point is x2, y2, right? Then this vector, let me call it, I don't know, what do you guys want to call it? A. Then A, this vector, is equal to x2 minus x1, y2 minus y1. So you just take the difference. And we don't, I try not to write the parentheses here. If this is a vector, we use angle brackets to indicate that it's a vector, right? So for example, if I'm going from, say, minus 2, 2 over to, say, 8 comma, 7, right? Then I can ask, what is this vector A? Well, then A is equal to, right, 8 minus a minus 2, and 7 minus 2. So the vector, yeah, is 10, 5. Right. So yeah, this you've got. All right, very good. Yes, very good. So notice that any vector, right, no matter what its base point is, you can imagine. So like, so there's minus 2, 2, right? If I was to clutter my picture and draw the xy coordinate system, where would it be? It's on there somewhere. It's down a little bit and it's over, right? So I will foolishly clutter my picture with the xy coordinate system, right? It's 2 over, it's 2 down. It's something like here is the, xy coordinate system, right? So clearly that vector is not based at the origin, right? But if you like, we can always imagine taking the vector, like this one, and we can take that vector and we can move it down to the origin, right? We can change the base point to the origin, and then we can find the standard angle for the vector, right? So, what's the standard angle? In other words, another way to look at this is you can imagine drawing a parallel line up here, right? And you can calculate the standard angle off that horizontal parallel line, like that. Whichever way you want to think about it, we can describe the direction of the vector by figuring out that angle, right? Whatever that angle is, that's going to tell you which direction the vector points. And you can also talk about how long the vector is, right? That's going to be the distance that the end of the vector is from the origin, right? So what's the magnitude? What's the standard angle? These are things we can discuss. for any vector in the plane. So for my example, let's calculate the magnitude, which is the length of the vector, and its direction, which you can take to be standard angle. So let's see here, what's the magnitude? So magnitude or length of a vector is denoted, and let's suppose that a vector is generically, say, a1, a2. So the length is denoted, so there's a couple different notations people use. The one is like this, double bars, indicates vector length. But in physics, a lot of times, you just write a. And that's the length of the vector. A with the letter with the vector over it, vector symbol over it is the vector. A is just a number. In fact, a positive number, which is given by the square root of a1 squared plus a2 squared. All right, but that number, whatever that is also the same as the distance from the base point to the terminal point for the vector, right? And so that's the magnitude, right? And then I think I've described what the standard angle is over here, right? We've already talked about this problem before. Let's work it out for the given example. Continuing example 1, what do we have? We have a is the square root of what? 10 squared plus 5 squared. So square root of 125, which is like 11.1-ish. Right. What's the standard angle? You could also use the notation, this angle, it's the angle, right, of vector A, if you like. There's a nice shorthand for it. That's not a common shorthand, but you could use it. Some calculators have something like that in their buttons. So where is this vector? It's in quadrant 1, right? So we can use inverse tangent of y over x in this case. In this case, inverse tangent of 5 over 10, right? And I like to use degrees for vectors, just a point of personal preference, but so we got. Yeah, inverse tangent of a half, so that's 26.57 degrees. So that gives you the direction of A as a standard angle, right? I guess while I'm at it, I'll calculate the square root of 125. What is it actually? 5 root 5. Thanks, calculator. It is 11.18. Ooh, see, I was off a little bit. Yeah. I remember that 11 squared is 121. That's how I knew it was close to 11. But anyway, surprised it's 11.2. Oh, I guess 144 is already 12, so it doesn't take long to get to 12 from 125. But anyway, so there you go, magnitude and direction. If you give me the magnitude and direction of a vector, I can tell you the vector. Example 2. Well, actually, first of all, theorem. If A has magnitude A and direction theta, in other words, standard counterclockwise, angle, then A is equal to a cosine theta, a sine theta. The proof of this theorem I can make on this picture over here. So it's just right triangle trigonometry, really polar coordinates. See, because if you look at the triangle, this magnitude is the hypotenuse. And so over here we have a sine theta. And down here we have a cosine theta. And so that means that A is just as advertised. And moreover, the fact that I've drawn the picture in quadrant 1 is immaterial because we know how sine and cosine play out in the other quadrants, right? They change to positive and negative as appropriate. Like in quadrant 2, cosine's negative, which makes the x component of the vector negative. In quadrant 3, both sine and cosine are negative, which means both the x component and the y component of the vector are negative. In quadrant 4, the x component's positive, the y component's negative, just like you like. I just introduced a word, component, right? So I should mention here, A1 and A2 are scalar components of A. Now, physicists and engineers also care about what are called vector components of a vector. Vector components are themselves vectors. Scalar components, the word scalar is another word for number in science, right? It also refers to sort of a transformation property of a physical variable, but for our purposes, just think scalar is number, right? So the scalar components of a vector, those are just the numbers that go into the x and the y components, all right, for today. We will do three-dimensional vectors in a future lecture. Then we'll have three components. We'll have an x and a y and a z. But to start with, let's do 2, all right? Okay, so we got magnitude, we've got, which is the length of the vector. We have the standard angle, which describes its direction. And you can go either way. I can start you with, the Cartesian components of the vector, and then we can get to the magnitude and standard angle. Or we can start with the magnitude and standard angle and write down the vector. Let's do that now that I've got this theorem. So example 2, right? If B has B equals to 2 and theta equals to 135 degrees, then what is V? Let's find its components and picture it. I'll start by picturing it. Picture it, 135, and second quadrant. So B is over here, like that. It has length 2, and it's pointing that way. What is it actually? I can use the theorem. B is 2 cosine of 135, 2 sine of 135, which is actually minus 2 over root 2, comma 2 over root 2. In other words, it's minus 1.4-ish, 41, comma 1.41. Because that's 45 degrees past 90, or 45 degrees above 180. So I know sine and cosine there have magnitude 1 over root 2, because I know my standard angles, Of course, you could use your calculator to find these things, right? Okay. So first things first, I tell you how to find the magnitude and the direction of the vector, right? But the next question you should ask is, what can we do with vectors, right? So one of the things we can do with vectors, I've already told you about, we can move them around, right? We have that freedom if we want. But another thing we can do is we can look at how to add them and subtract them and even multiply them by a number. All right? So I will actually give you definitions which are not geometric, which are algebraic, because the algebraic definitions are very simple and easy to work with. And once I tell you the algebraic definitions, then we can take the geometric results as sort of theorems, if you will, necessary consequences. So here's definition. If we have A is A1, A2, and B is B1, B2, then A plus B is A1 plus B1, A2 plus B2. So in other words, to add vectors, you just add components. And if C is a real number, then CA is CA1, CA2. So this is called the scalar multiple of A by C. So before I say anything more, I'll give you an example. Let's let A equal to like 4, 1, B equal to, I'll make it easy, 0, 3. All right. All right, A plus B is 4 plus 0, 1 plus 3, which is what? 4, 4, right? And I guess, if you don't mind me being lazy, minus, minus, minus. Like if you take the difference of vectors, you just take the difference of the corresponding components. So that's how you do that. So like A minus B (4 minus 0), 1 minus 3, right? Did I do it? Yeah. You got to be careful with subtraction because it matters which one is which, right? Subtraction does not commute. So we got 4 and minus 2. Let's draw a picture. What's going on here?
Where does C go?
Oh, I didn't do anything with C yet. I'll do that. I'll do that next. Let's see here. So suppose this is 4 units out. Oh, let me make my picture bigger. I always don't leave myself room for the thing I need to show if I'm not careful. Okay, so suppose that this is 4 units over. Suppose that this is 4 units up, right? So here's 2, here's 2, here's minus 4, there's minus 2. All right, so A, it goes to here, right? It goes 4 over, 1 up. So A looks like this, right? And B, what's B look like? Well, B is 0, 3. So that's a vertical vector. It goes up to here.
You drop them all, A?
I drew it that way on purpose. So this is the way to understand them geometrically. If you want to understand what A plus B is geometrically, you draw them tip to tail. So you start, pick the starting point, go A, and then travel further by B. And then what is A plus B? Well, geometrically, it's whatever it took to get from the initial starting point to the final ending point. Over here is A plus B. So this is known as tip to tail. Vector addition. What's that?
Would it shift 1 unit to the right and 3 units up?
Oh, B is 0, 3, though.
Oh, 0.
Yeah. You put a 1 in there? Yeah, that's understandable. Let's see here. Now, a minus b, yeah, so a minus b, so instead of going up, let me draw it over here. So, so we have a like this, right? And then b goes, well, minus b goes like that. Now, so minus b is minus 1 times b, which is 0 minus 3. So it's the same. So I can think of subtracting b as adding minus b. But minus b, what that is it flips the vector over the pole, like it reverses the direction. And so that's why we got 4 minus 2 here. Obviously, I haven't tried, I have not done it just here. Let me fix it. I'll sort of fix it, but at the other hand, I mean, there's no good way to fix it, but here's my poor attempt at fixing it. Because A is supposed to be 1 unit up, and minus B is 2 units down below the x-axis. This should be 1.
I get that.
This should be 2, but see, now that I've done this, it's not, it's skew. I mean,
Why will we move it down 3 units and not 2? Like when we did A.
well, minus B goes down 3.
Oh, yeah.
So we need one to get to the x-axis and another 2 to finish the job.
I was looking at your A minus B like the finish point.
So, yeah, I mean, so anyway, geometrically, to add vectors, we add them tip to tail, all right? Algebraically, you just find their Cartesian components and add them. So, you know, it's not bad, is it? All right. Let me give you another example. So let's see here. Suppose you got point P, you got point Q, you got point R, right? Then PQ is Q minus P. QR is R minus Q, and RP is P minus R. So this notation you may or may not have seen in like high school geometry. We use the term, you're explicitly writing the base and the terminal point of the vector as P and Q here, and then the formula for the components of the vector is the difference of the points. So like, you know, this would be, if you like, Q1 minus P1, Q2 minus P2, you know? Supposing that Q has, you know, coordinates Q1, Q2. So my question to you is, what is the sum of these 3 vectors? What is PQ plus QR plus RP? Well, I mean, I can write it in terms of just the point notation. It's Q minus P, right? Plus R minus Q plus P minus R, right? And yes, I could get into the 1 and 2 component stuff if I wanted to, right? But that doesn't really help with this example. I could write it out. We'd be writing it for the next 3 minutes. We wouldn't add anything. the point is that you can do calculations like this, and if you do, see what happens? Q and minus Q cancel, right? P and R, and we get 0, yeah. And why is that completely unsurprising? Well, let's think about the tip-to-tail addition, right? We have vector PQ, right, plus vector QR plus vector RP. So if we do that, tip-to-tail addition gets us right back where we started. So this is part of like of a more general theorem. If you take the vectors which sort of surround any sort of closed geometric shape that has flat sides, like it could be this, whatever, right? If I take vectors that, pick one point, if I take like this vector, plus this vector, plus this vector, plus this vector, plus this vector, say A, B, C, D, E, then in this case, A plus B plus C plus D plus E, it's 0. So it's just a fun thing to think about. Now in physics, we use vectors to describe forces, right? So it could be something like this, right? You've got a car, and you've got one group of people. I mean, you got a bear. There's a bear, right? And he's pulling on it this way, right? Chain. And then over here you've got a lion, right? And he's pulling on it straight down. And then over here you have school children. And they're pulling on it this way, right? And you have these three forces, F1, F2, F3, and you can say, well, what's the net force on the car? Who's going to win, the bear, the lion, or the children? No one wins. But if you wanted to find the net force, what do? The net force is F1 plus F2 plus F3, right? And if those, if those forces are actually pictures that are accurate in terms of the length of vectors to describe those forces, then you can just do those tip to tail, and that would tell you the net force. And if there's nothing else in play, then that would tell you which way the car is sliding. Because ultimately F is equal to ma, so you find the mass of the car, and that would tell you the acceleration.
Could that be 0, though? The bear's pulling up and right.
Yeah.
The children are pulling right at the same.
Oh, sure. It could be 0. It could be 0 if the horizontal component of the bear matches the force of the children, and if the vertical component of the bear matches the force of the lion. Because I've pictured the lion force and the children force as respectively vertical and horizontal. Anyway, just like I was saying, like to actually figure out the net force, you would do something like bear, F2, and then add F3 would be like this, right? And then F1 maybe would be like this, whatever. If that was the case, if the actual picture was this in terms of magnitude, that would mean that the lion's winning. It's sliding down. See, because the net force, which is the resultant of the sum of the forces here, would be F net. All right. Okay, so I would argue that like adding vectors either geometrically or with algebra, this is not too hard of a problem, right? We can do this. So the next thing I would introduce to you is another description of the direction, all right? I would introduce you to what are called unit vectors. What's a unit vector? So a unit vector is a vector of length 1. All right, that's what a unit vector is. It's a vector of length 1. So here's the theorem. If A is not equal to 0, then if I let U, well, I'll just say this, then 1 over the length of A times A is unit vector. So here's the proof. So let's let A equal to A comma B for our convenience of this proof. Okay? If A is A comma B in terms of components, what's the length of A? Square root of A squared plus B squared, right? So what is 1 over A times A? Right? Which then, by definition of scalar multiplication, is A over So let's find the length. What's the length of 1 over A times A? It's the square root, right, of A over the square root of A squared plus B squared plus B over the square root of A squared plus B squared, which is also known as the square root of A squared plus B squared over A squared plus B squared. So whenever my 4-year-old burps, he immediately goes, "Excuse me," and then he says, "I'm the king." And if you burp and then you say, "Excuse me, I'm the king," he'll say, "No, you're not little." No, you're not little. You can't be the king. And if you fake burp, he'll just be like, "You just did that with your mouth. It doesn't count." His system of, his form of government is, not widely known, and really enforced by the dictate of his cuteness. But anyway, how do I know that this division makes sense? Well, remember, I assumed that the vector was non-zero. If the vector is non-zero, it has non-zero length, which means that A squared plus B squared is non-zero. For a vector to be non-zero, it means at least one of A or B has to be non-zero. Hence, A squared plus B squared is non-zero, and this is just 1, which shows you that 1 over the magnitude times the vector is a vector of length 1. Now, we have a notation for this, all right? So, definition, A not equal to 0 has a hat equal to 1 over A times A. So this is the unit vector in direction of A, right? And notice that you have an immediate corollary to this theorem, if you will. A not equal to 0 has a vector equal to A times A hat. In other words, any vector can be written as a product of its magnitude and direction. Magnitude or length, direction, as unit vector. What is the connection between the unit vector and the standard angle? Well, if you put everything we've done together today, you can see that A hat should literally be cosine theta sine theta, right? It has to be that. because we before had the vector written how? So if you want to describe the direction of a vector in the plane, you got two choices. You can either give the standard angle to describe its direction, or you can give a unit vector to describe its direction. These are in one-to-one correspondence. You give me standard angle, I give you a unit vector. You give me, unit vector, I give you standard angle. One example here. If we have A equal to, say, 3, 4, then the magnitude of A is square root of 9 plus 16, which is the square root of 25, which is 5. So the unit vector of A is 3/5, 4/5. So next up, we'll talk about how to find the angle between vectors, okay? So hopefully Friday. Thanks, guys. Don't forget, your take-home quiz is due Friday.